Yeah, so I'm going to have some movies to distract you while I'm talking. This is the first of those. This is a movie I did for a planetarium show back in 2016 or so. Anyway, the title of my talk is Numerical Simulations of Planetesimal Formation. And it's a sort of decidedly generic title because this talk is sort of going to be an overview of research that I've done over the past 3 or 4 years, as well as a very sort of preliminary, speculative, forward-looking research plan. Um, and so I'm going to touch on a few topics, but not in any terrible depth. But you can, of course, ask me questions afterwards and at the coffee break. All right, so I press green to go, right? Okay, good. So we all know that planetesimal formation is a difficult thing. I don't really have to explain any of the introductory stuff here, but I'm going to a little bit anyway. Planetesimal formation is subject to growth barriers. We know that you can build up to about millimeter or centimeter sizes, but once you reach those sizes, oftentimes the radial drift takes away these objects into the central sun, central star, at a much shorter lifetime than much shorter time scale than the lifetime of the disk. But even if you could get around that somehow, you might have trouble growing these millimeter, centimeter size objects to bigger than that. This is shown through lab experiments by a German group, Vermin Bloom, I think is the correct reference. I'm sorry I didn't put that there. So how does one get around these? That's a big question that we try to answer in understanding planetesimal formation. There's sort of two schools of thought. There's the bottom-up growth picture, which I'm not involved in, so I'm just going to sort of put this up here and just maybe briefly say a few words. But the idea is that maybe there are some ways to get around the radial drift barrier and these fragmentation or bouncing barriers, such as maybe if you have fluffy ices instead of silicates, they'll be easier to stick together, and they can stick together sufficiently rapidly that they could grow into larger objects. Although there's some recent work by the German group again that suggests that the sticking efficiency for ices is still pretty low. I mean, it's about the same as it is for silicates, so that's a little discouraging for that model. But there's some other possibilities for getting around that, and I'm not going to spend any time on that because, again, it's not my field, and I don't have time for a full review talk. It's more of a what I'm doing talk, I guess. But the other school of thought is top-down, that you somehow concentrate, let's see, if I press this, will it play? Good. If you somehow concentrate enough of these centimeter, millimeter sized pebbles into a small enough region, then the Roche density will be reached. Gravity wins over shear, and collapse ensues. And this is one of our favorite mechanisms for doing so, something called the streaming instability. This is just a small local shearing box here. And if you account for momentum exchange between gas and dust, you get these nearly axisymmetric structures. I'll try to play it again. Oops. Nope. Okay. You get these nearly axisymmetric structures of overdensities in the particle mass density, surface particle density, that can collapse and produce planetesimals. Another way, if you just sort of throw out for a moment the idea of momentum exchange and just assume that the particles are feeling drag from the gas, you can collect particles into certain traps. And one idea is that if you have these pressure bumps in disks, which now there's observational evidence that this is happening, you can concentrate enough particles into the traps that maybe they don't even have to go streaming unstable, but they'll just go above the Roche density and collapse. Another possibility is vortices. I'll be talking a little bit more about pressure traps towards the end of the talk. Okay, but I think Hannah yesterday said it behooves us to think about observations, and I'm certainly a theorist through and through, so I'm not going to claim any expertise on observations, but what I will say is that it's very important that we compare our models to them, and I don't think I'm saying anything new here, but in the context of this work, one of the best comparisons, well, first of all, we're sort of stuck with the solar system because it's nearly it's impossible, basically, to directly observe planetesimals in other solar systems. Maybe there's some indirect ways, but I haven't been able to figure that out. But we have our own planetesimals in our solar system. The cold classical Kuiper belt, which is a mouthful, is the best one probably to observe because it's pristine, relatively pristine. It's nice dynamically cold orbits, and we think that these are a reflection of the initial population of planetesimals at that distance. And so one common thing that is done in the literature is to compare the size distribution of planetesimals, or equivalently the mass distribution of planetesimals, to that in theory. So for the rest of the talk, I'll probably be, or for most of the rest of the talk, I'll be talking about the mass distribution. I put size distribution up here because this is sort of where observers and theorists come together, because observers always put things in terms of annoying magnitude distributions, and I can't think that way, but I can think in sizes, and so can observers, so we go on with that. So yeah, the goal ultimately of this work that I've been doing for so many years, well not so many, but some years, is to carry out numerical simulations of planetesimal formation and compare with observations. And again, I've been focusing on top-down mechanism. You can talk to Hilke Schlichting for the sort of other ideas for forming planetesimals and how that compares with observations as well, but I'm not going to get into that. And just to set the stage, I use the local shearing box approximation with the Athena code, Athena gas dynamics code that has particles included as well as particle self-gravity. I really don't need to explain this other than to just say that the streaming instability and these related processes happen on scales much less than h, making this a very useful, if not somewhat essential, unless you go to really high resolution, tool for studying these processes. Okay, and just because I like movies, I'm going to show another one. This is a movie, the same thing I was showing you before, but now the streaming instability has produced these overdensities, and you get bound objects forming once the Roche density has been reached. This is work that I'm involved with, David Nizvorny at SWIRI, and it's just been accepted to Nature Astronomy. I'll get into why it's a cool result other than this movie eventually, but I'm going to play it again. Yeah, so this is just to show you that we've done a number of these calculations now. We find bound objects in our code, and we analyze them. We look at their properties. And one of the, again, one of the best things to do is compare the mass/size distributions of those formed in our simulations to those in observations. But as a true theorist, I have to think about the relevant parameters. That's always what we want to do. And we like to make dimensionless ones so that we don't care about units too much. And there are sort of four relevant physical parameters that control the outcome of this sort of whole system. The last, well, I'll just start with the obvious one. This is the strength of gravity relative to tidal shear, or somewhat weirdly G tilde, which I must say I didn't take credit for using that term, but I have adopted it and I haven't changed since then because I don't like change. But this is basically just the strength of gravity relative to tidal shear. It's obvious to that it'll be relevant for collapse, and it's basically it'll come up eventually. Let me just do that. It's just inversely proportional to the Turmeric Q. So maybe I should go back in all the literature that I've done and change it to be Q instead of G tilde, but whatever. This is the point that's the relevant quantity for collapse. And just to push that away, the other three are more relevant to the nonlinear, fully developed state of the streaming instability. One is the particle size, which we quantify here. Sorry, this is so close to the edge. As the dimensionless stopping time. The other is the ratio of solid surface density to gas surface density, Z here. Sometimes referred to as the metallicity, though not always accurately, and then the dimensionless radial pressure gradient, which is an important parameter because this actually is what's responsible for driving the physics of the streaming instability itself. Okay, so let's just jump into some results. Actually, I'm starting with the newest results first, and I'll sort of go backwards in a way. But this is some work that my undergrad, who's just now graduating and going to UNLV, we were just about to resubmit this paper. It had a pretty good but detailed referee report. Anyway, you don't care about that. The point is that we have quantified the mass function, and we find a power law. If you fit it with a power law, P is approximately 1.6. And this is for different radial pressure gradients. We couldn't vary the radial pressure gradient too much because, well, there was a very well, never. I'm not going to get into the details, but basically, if you put the pi too high, the system became so turbulent you couldn't form planetesimals in the first place. So we had a very narrow range to work with. But nonetheless, we found p is approximately 1.6. But sort of going backwards in time now, I've looked at this parameter p for in a number of different contexts. My first paper on this this should be g tilde, not g, but there we go again. This is, I've looked at g tilde. We looked at in 2017, the tau at different z values as well, and then again, most recently with the different pi values. And we always seem to find, at least within sort of the error bars of 1 or 2 sigma, that p is approximately 1.6, maybe sometimes 1.5. And, why? Well, before I say why that is, or why I think it is, I'm going to just point out that we weren't the only ones to see this. This sort of validates it in a sense that the Pencil Code also carried out simulations, and in the Science Advances paper by Johansson, 2015, they also found, here p is their QM, of approximately 1.6. So it's an annoyingly well, I don't know if annoying is the right word, but it's a consistent value no matter what we change the parameters to. But is it actually the right parameter to use to describe the mass function? Recently, so the reason why we've recently started to think maybe it's not is that we have a much better, thanks to my collaborator Urshan Lee at the University of Arizona, we have a much better clump finding algorithm than what we originally had. It does a very good job. And so we were able to determine planetesimals over a huge range of masses and really improve our statistics. And what we find is if you look at, so it's easy to see sort of something like a power law in the differential mass, but even here there's some indication of turnover. If you look in the cumulative mass function, you see that it's clearly not just one power law. And we're not sure what the best function to fit this is. There's a paper coming out, I'm on it, but Urshan Lee is the lead, where he tries different fitting functions and calculates the best fit. But for right now, for the paper that my undergrad did, we just assumed a simple exponentially truncated mass function, which in the form of the cumulative mass function is written like that. And in that case, we find p prime here, which is the equivalent to p, but now in this new fit, is approximately 1.3, which is shallower basically because, well, partially because of the fact that now we have this curvature to account for, and it goes over a reasonably large range in mass, but also there's some flattening of the distribution up there. So it's not even clear that you can say it's just a power law with an exponential truncation, but maybe you can. I will say, read the paper for more details, especially the upcoming paper, to see how good a fit it is. Okay, but the point here is not so much what the value of p or p prime is. The shape of the mass, the point is that the shape of the mass function seems to be only weakly dependent on relevant parameters. So p or p prime doesn't seem to change much no matter what we change the parameters to. But how does this actually compare with observations? I've gone on and on about this, but that's all theory. What about observations? So this is also a plot from that paper that we recently submitted to APCHE. This is showing the slope, or the local p-value. I shouldn't say local, but basically this is the p-value, or p prime equivalently, of a mass function for different planetesimal sizes in diameter here. So just to point out a couple of things, I'm actually not going to focus on the very high mass n for right now, but I want to just point out the cold TNOs here are the ones that are probably the best representation. Those are the cold classicals that I was talking about. So these are probably the best ones to trust here. And well, it's interesting because 1.6 does align with those planetesimals, but annoyingly, in the more realistic fit, we find that it's actually shallower, and it doesn't agree with that. And so a shallower slope in our simulations compared to observations suggests, well, I mean, unless the observations are wrong, which is possible, maybe something is wrong in our model. And one possibility, maybe, is that, I'm putting both of these up here, that maybe there's a resolution effect at the lowest mass end. It's somewhat speculative, and we haven't looked into this yet. But if you look at this, p of 1.6 just by eye reasonably fits the low mass end, but then you start to get this turnover at the very low mass end. Perhaps if you go to higher resolution, this would go up a little bit as you form more and more planetesimals at smaller scales. And that needs to be tested. But if that holds up and we get and we get a larger range in masses from the highest to the lowest than maybe a p prime of 1.6 with an exponential truncation would be reasonable. The other thing is to consider more realistic setups. These are highly idealized numerical simulations where we have a shearing box and we set the particles going in there, and we have some already increased z value, and we have everything properly set up for planetesimal formation, but there are things that we neglect. And one thing is turbulence. Now, whether or not there's turbulence in disks is a big open question, but at the very least, we know that there probably is some small amount of turbulence, alpha times 10 to the minus 4 or so. And so I did this is very, very preliminary, and my grad student, who's sadly graduating as well, is working with me on this as his last hurrah at Colorado. But this is a proof of concept I did for a proposal, actually, where I forced turbulence into a shearing box at about alpha 10 to the minus 4, so it's not too strong. And I measured the mass function slope, again going back to the simple p here, of 2.2 plus or minus 0.2, the error, compared to no forced turbulence of 1.6. Now this was an older result. It didn't have that advanced clump finding algorithm, hence the statistics aren't as good. So this needs to be looked at further, but it's intriguing, right? I mean, does this mean if we have turbulence and it makes things steeper, will it make the cumulative looking mass function look different and not so shallow on the low mass end? Very preliminary. So yeah, so at this point, well, never mind, I'm not going to say that. But I want to just sort of touch on that a little bit more by saying one idea that we had in 2017 was that maybe all the p-values are the same, the shape of the mass function is the same is because the turbulence that's generated by the streaming instability, maybe it's also the same. So the nonlinear fluctuations in the turbulence are somehow have the same power spectrum, and we don't really understand completely why that is, why that doesn't change with the parameters, but that might be responsible for seeding the same mass function if there's a direct relation between the nonlinear structures in the turbulence compared to the mass and the mass function itself. And so we looked a little bit just briefly into this. This is the power spectrum of the mass density compared to the k value in Fourier space. We find roughly the same shape, although there is some moderate differences there. So that remains to be investigated in a little bit more detail. But now I'm going to sort of take a step back from what we have done and talk a little bit about what we've really most recently done and what we'll do in the near future. And I also want to point out that instead of just the mass function, there are other diagnostics that we can employ, especially now with New Horizons, I have a joint position at Southwest Research right now, and I get to hear about all the good news about New Horizons and producing these beautiful images of MU69, aka Ultima Thule. And this, sadly, is not an image, but just a reconstruction of what it should look like, but it's nice and flat, like a peanut or a walnut, or not a peanut, but like a walnut or something like that. Anyway, the point is we have these interesting structures now, and we seem to see that they're in binaries. A lot of them are either in contact binaries or wide binaries. And so trying to understand planetesimal formation in that context is also another way to constrain our theories. Go forward. Okay, so this is the stuff that got accepted to Nature Astronomy. We looked at the angular momentum in our clumps as they were collapsing, or as they collapsed, and basically found that they had a ton of angular momentum. Now, they didn't separate into binaries because of resolution conditions. Basically, these things don't collapse all the way down because of the gravity sort of halts things at the grid scale for numerical reasons I won't get into. But we looked at the angular momentum distribution and found that almost all planetesimals lie above J crit. J crit is when they should fragment into two or more objects. So that's interesting. So we looked at the obliquity, basically the vector of the angular momentum compared to just the top, the vertical direction of the disk, and compared it to obliquities of binaries in the cold classical Kuiper belt, which is recently, which I think is going to be published in Icarus by Will Grundy's group. And basically, we found a very, very good match, and we found that nearly 80% of binaries are prograde, which is in agreement with observations. And within that prograde population, it's very widely spread over this inclination distribution here. So that's an interesting result because it suggests that at least for the streaming instability, binary planetesimal properties are very consistent with what is observed. And so some more work needs to be done there as well, but that's sort of the main point there. Now I'm going to get into stuff that's even more speculative in the last few minutes, and I should say maybe not more speculative, but more hot off the supercomputer, hot off the presses, and that is to talk about a little bit more about pressure traps. And I was not, I didn't put any effort in just finding the most recent ALMA images, so I just went back to the original one, but it's still, the one that made everyone's jaw drop, so just motivating it further, we know that these pressure traps exist in disks, and they're trapping dust particles, and the notion here is that, we all know that pebbles drift towards pressure maximum, but it could be that they get to pressure maximum and they just collapse due to gravitational instability without even going through the streaming instability, but they might also go through the streaming instability process. So this is a parameter space plot by Daniel Carrera and modified by Qiuqin Yang a year later, showing regions of particle size tau and concentration z, where pink is you get no streaming instability, but green is where you get streaming instability. If the pressure trap can concentrate particles enough to push it into the streaming unstable regime, but not enough to go directly gravitationally unstable, then you get sort of you get help from the pressure trap to go streaming unstable, and then the streaming instability will take over from there. It's not clear yet which one would come into play, but that's sort of a spoiler. But what I have done is run simulations with a pressure trap. These are local simulations with a pressure trap included, let particles drift into the pressure trap and see what happens. So I was going to say, I don't yet know if it's streaming instability producing these planetesimals or direct collapse. I think it's direct collapse, but I don't know yet. It's very, very, very preliminary. But what I did say is we looked. This looks like a galaxy, it's not, but we looked at the structure of some of the planetesimals. In fact, this was a relatively low resolution run, so we looked at all of the planetesimals. There were like 20 of them, and there were a few false positives in there, but all of the real planetesimals have this sort of structure. They're very, very flat, and I'm going to just advance to show you other ones that continue to rotate around. They all have this flat and sort of streamy looking structure. It's kind of weird and really cool. So what's going on here, I don't know yet, but it sort of piqued my interest. I showed this to Phil once, and he's like, whoa, this reminds me of MU69. I'm like, yep, my thought as well. So, oops, go backwards. Is there a potential connection between flattened planetesimals and what we see in our simulations? Speculative, maybe. The problem is that these planetesimals, like I said before, they're sort of halted at the grid scale. The way that the gravity is done in these codes, it doesn't really allow particles or planetesimals to continue their collapse to smaller scales. You can see here, this is one such planetesimal looking down on it, and these are grid cells, and it only spans a few of them in diameter. So what would happen if you allowed them to collapse further? Would you get the needed 4 orders of magnitude decrease, and would you maintain sort of the same flatness as you shrunk? And also, would you get a binary that then forms from that and then loses enough of its angular momentum, perhaps through collisions or gravitational torques from these spiral structures, to then coalesce and sort of form this contact binary? Speculative, I know, but we're following it up with simulations from this PKDGRAV. I'm working with people, David Nizvorny and Raphael Marshall at Southwest Research, who know how to do this stuff to understand it further. Now, we don't have any movies yet, so I'm just going to show an old one from David Nizvorny in 2010, just to demonstrate this doesn't have any restrictions due to the grid. This is just like this is a tree code, and so basically what we do is we just directly export the flat planetesimals from Athena and put them into PKDGRAV, and thankfully there's only 20 of them, so we don't have to worry too much about statistics. Well, it's poor statistics, but we can probably run all of those with PKDGRAV and get some idea of what's happening. So that's a very interesting area, and I'm almost done. All right, and so what was I going to say? All right. I'm not sure if that was, oh yeah, so I guess the question for discussion is, how do the predictions from the bottom-up models compare with these observations? So I've talked so far about all this stuff from top-down collapse, but I would like to hear more, if not anything for just my own education, how the bottom-up models compare with these observations. Is there anything to learn from that? And so then I arrive, alas, at my last slide. There's a weak dependence of the mass function on the relevant parameters. It seems that P is approximately 1.6 or so. There's some tentative evidence that turbulence may change that, but we don't know yet. Properties of binary KBOs are consistent with the streaming calculations, which is very interesting. And then pressure trap simulations show flattened planetesimals. I don't know yet why they're flattened. I think they have an excess of angular momentum. That still needs to be verified too. This is all very fresh. And it suggests a possible connection to MU69. So with 4 minutes and 30 seconds left, I'm finished.
You turn over.
Oh, of the simulations,
yeah.
or the? Yep, that'll get there eventually. This thing doesn't.
Yes.
Okay.
So you alluded to the fact that you're possibly concerned that there may be some numerical effects that determine the lower end shallowing. I'm curious, are you confident that the high end is real? And if it's real, what's the physical reason for this overturn? Or could it be also that it's a limitation of the size of your simulation or something else numerical?
That's also a possibility. Yes, we have not played around with box size or anything like that, so that could play a role. We have. I mean, I don't know if you're questioning the fit, which is admittedly not as good at the high end, partially due to the poor statistics there, or something else.
No, I'm not worried about the fit. I'm really curious whether that's a real physical turnover that you find rather than that power law. And if it is real, I would love to know what's the physics behind it.
Right. Yeah, we don't know. Yeah, sorry to say.
On the question of the low end of the size distribution, I thought there was some evidence recently from cratering on, was it Pluto? For claimed evidence for turnover in the size distribution at low sizes.
Right.
It's a deficit of small craters, and the authors believe that resurfacing is unlikely.
Right.
Of course, you also have to fold in a model for how the size of the planetesimal relates to the size of the crater, but that's fairly non-controversial.
Right. You're talking about the Singer et al. 2019, I think.
Probably.
Yeah.
And then there was something else which I forget, which came out for some other body. But anyway.
Right.
Could you comment?
It's an interesting possibility. The only thing I would say there is that the smallest planetesimals we form are bigger than what they can put on their constraints. There's a large, I don't know how large, but there's a large mass difference there between sort of their largest craters and our smallest planetesimals.
In the PKDGRAV simulations, have you determined that gas drag is no longer relevant to the dynamics?
Yes, it doesn't seem to be relevant.
Make a little bit comment about the high-end cutoff. We looked at this already earlier. Because the mass function is very top-heavy, so a lot of pebble accretions is onto the largest bodies. So there must be a cutoff. And then how do you decide the characteristic cutoff is actually determined that by the total mass budget in the filaments itself. So you will clearly see the correlation between the mass budget in one filament to the mass of the heaviest object. So that's all I can comment about this higher mass end.
But does that explain the fact that it's a truncate, or what produces that very...
It's not clear about the shallow cutoff. It's not clear, but just as you say, that it's not a very good fit, but at least we know it's a shallower cutoff. But we do only observe quite a small number of largest objects. That's the result.
Yep.
So commenting still if you look at the plot that you just have up, the mg thing, right? So it looks like all these distributions go up to mg equal 1 or 2. This mg you can just derive taking the critical wavelength from the Turbulence dispersion relation, and then you put your pebble surface density in there, and then you get exactly the mg. And I think this is the basic physics, actually.
Yes, except that we now have some results where we find planetesimals at 100 mg.
Okay,
so we
that's
don't.
Amazing, then.
Yeah.
But what did you change? Did you change the box size, or?
What were those differences? Those were just different tau and different z, I believe, than the ones in these simulations. It's almost like we got lucky here, because we didn't vary tau or z in these simulations. Obviously, we just varied the radial pressure gradient. But my colleague Urshan Lee went back and looked at the other simulations where we hadn't yet used mg as a scaling, but we had a fixed pi, but different tau and z, and found different masses in units of mg.
I think that would be great for pebble accretion, because this mg is a little bit too small to pick up pebble accretion from that.
Your simulation with pressure bumps, presumably the planetesimals are sort of flattened. But you also said in more typical streaming instability simulation, you have a lot of angular momentum.
Right.
Are those also flattened?
That's a good question. Some of them are, but not nearly to that extent. And I don't understand why that is either. Part of it seems, is that things settle a lot in the pressure drop simulations before they form planetesimals, as opposed to the streaming instability where they sort of become turbulent as a part. Yeah, exactly. But I'm not 100% confident of that. Oops, there we go.
Okay, I think we should stop there. And thank you, Jake.
Thanks.